For centuries, when we looked out into the solar system, Saturn appeared as a serene, silent masterpiece. It seemed to be a simple, static sphere of gas, wrapped in pristine icy rings. It orbits 1.4 billion kilometers from the Sun, existing as a behemoth 9 times wider than Earth. To understand that scale, look at its volume. Saturn is large enough to swallow 764 Earths before filling its transparent silhouette. Despite that massive volume, it has a density of only 0.687 grams per cubic centimeter. It is the only planet in the solar system less dense than liquid water, meaning it would actually float if placed in a large enough ocean. Its rapid 10.6-hour rotation generates intense centrifugal forces. This high angular velocity causes the planet to visibly bulge at its equator and flatten at its poles. We have observed this giant for centuries, but modern instruments have revealed a reality that proves our foundational assumptions about its structure were entirely wrong. Scientists previously assumed that Saturn formed around a discrete, highly dense, solid rocky core at its center. To test this, researchers used chronoseismology. They treated the rings as a giant seismograph, reading the spiral ripples caused by gravitational pulses sent out from the planet's sloshing heart. Instead of a solid core, they found a fuzzy, slushy soup of ice, rock, and metallic fluid. This diffuse interior spans 60% of the planet's diameter, gradually mixing into the hydrogen and helium layers above it. This core is fueled by helium rain. Sinking droplets of helium release gravitational energy as they descend, explaining why Saturn radiates 2.5 times more energy into space than it receives from the Sun. This stable, sloshing gradient suggests that solids and gases may have accumulated in tandem, challenging the theory that a solid core must form first to attract a gaseous envelope. That internal heat powers violent meteorology in the outer atmosphere, where equatorial winds reach 1,800 kilometers per hour. These shear forces create the North Polar hexagon, a persistent 6-sided jet stream wide enough to fit 2 Earths. In laboratory simulations, these stable polygons naturally form at the boundary between fluids rotating at 2 different speeds. At the center of this hexagon lies a hurricane-like vortex with an eye 50 times larger than a typical terrestrial hurricane. The atmosphere also undergoes seasonal shifts. As the pole approaches summer, ultraviolet sunlight triggers the production of photochemical smog, turning the region from blue to a yellowish ochre. Without a solid landmass to disrupt them, these geometric atmospheric features persist for decades, providing a direct look at fluid dynamics on a planetary scale. The iconic rings were once thought to be primordial, forming 4.5 billion years ago alongside the planet. They are incredibly thin, averaging only 10 to 100 meters in vertical height. Small shepherd moons embedded in the system actively maintain this architecture, using their gravity to carve gaps and waves within the ice. Because the rings are so clean and bright, they are likely only 10 to 100 million years old. They may be the shattered remnants of a former moon that drifted too close to the planet and was torn apart. This material is now being lost to ring rain. Magnetic fields pull charged water particles into the atmosphere, siphoning thousands of kilograms of material away every second. At this rate, the rings will disappear entirely in a few 100 million years. Our current view of Saturn is a temporary coincidence of cosmic timing. Moving past the rings, we find a satellite system that has evolved from a collection of inert rocks into a diverse mini-solar system. This collection includes the two-toned Iapetus, the crater-scarred Mimas, and saucer-shaped moons Pan and Atlas, which built their ridges by sweeping up ring dust. Saturn's largest moon, Titan, possesses a thick nitrogen atmosphere and an active cycle of liquid methane lakes and rivers. The tiny moon Enceladus is even more active, erupting massive plumes of water vapor and ice from fissures known as tiger stripes. These plumes originate from a global subsurface ocean that contains molecular hydrogen and complex organic compounds, suggesting the presence of hydrothermal vents on the seafloor. The discovery of these environments has shifted the search for life away from planetary surfaces to the warm, hidden oceans of icy moons. This understanding of the Saturnian system is the result of the Cassini-Huygens mission, which provided 13 years of high-resolution in situ data. Cassini's observations of planet-encircling storms and active geysers revealed an evolving laboratory for planetary formation and chemistry. With the rings raining into the atmosphere and the moons harboring chemical oceans, we exist in the specific sliver of time required to witness this system in its most complex state.